With a single autosomal locus, genotype frequencies in the ideal population reach equilibrium after one generation of random mating. I'm Mohammad Sahebhonar, and in this lecture I want to expand the Hardy-Weinberg analysis to consider a pair of loci simultaneously. Within a given population, the non-random sharing of alleles at different loci in a gamete is called gametic phase disequilibrium, or misleadingly linkage disequilibrium. Why the term linkage disequilibrium is misleading? The loci may be physically linked on the same chromosome or located on different chromosomes. In addition to the linkage, selection favoring one combination of alleles over another, genetic drift in a small population, and intermixture of populations with different allele frequencies can arise disequilibrium, or in other words, allelic association. In this case, a specific allele at the first locus is associated with a specific allele at the second locus more often than expected by chance. Consider a population for 15 discrete generations. Consists of 100,000 diploid individuals in each generation. Half of them are males. There are two diallelic autosomal loci, A and B, that are in gametic phase disequilibrium. For the first scenario, both loci have equal allele frequencies. The initial allele frequencies for big A at the first locus and big B at the second locus is 0.5. The recombination rate between them also equals to 0.5. In contrast to the previous lectures, here we consider the frequency of gametes instead of zygotes in each generation. The four possible gametes are big A, big B, big A, little b, little a, big B, and little a, little b. If the population were in gametic phase equilibrium, we would expect the alleles at these two loci to segregate independently. Therefore, based on the initial allele frequencies, we expected to see an equal proportion of each gamete. For a single locus, gamete and allele frequencies were the same. For a pair of loci, this is not true. The equations indicate the relationship between allele and gamete frequencies. For instance, the frequency of big A is the frequency of big A, big B gametes plus the frequency of big A, little b gametes, and so on. The allele frequencies are constant from generation to the next, but recombination creates new gametes in the following generations. The expected frequency of a given gamete in the next generation is the frequency of the gamete in the current generation plus or minus the recombination rate multiplied by the disequilibrium coefficient. The disequilibrium coefficient measures the difference between observed and expected gametes. The first term in the equation is the frequency of gametes that contain big A, big B. The second term is the allele frequency of big A at the first locus times the allele frequency of big B at the second locus. The maximum value of D is 0.25 when big A, big B and little b are the only gametes present, and each has a frequency of 0.5. Similar to this situation, the minimum value of D is negative 0.25 when big A, little b and little a, big B are the only gametes present, and each is at a frequency of 0.5. If D equals 0, the population is in gametic phase equilibrium. One drawback of the metric D is that it depends on allele frequencies. To show what I mean, let's run the simulation again. But this time, I want to set the initial allele frequency for both loci to 0.7. As the result shows, the value of D decreased to 0.21. Let's run the simulation again, but in this run, I want to set the initial allele frequency for big A and big B to 0.1. Although the two loci are still in complete disequilibrium, the value of D is 0.09. Therefore, other measurements that are less dependent on allele frequencies are more desirable. The next measurement is the correlation coefficient, which is equal to D divided by the square root of the product of the allele frequencies at the two loci. The correlation coefficient can take a range of values from -1 to 1. It's noteworthy that the sign of the correlation coefficient depends on the sign of D. The value of 1 means that the population is in complete disequilibrium. Statistically speaking, D is the covariance in allelic value between the loci, which is normalized with respect to allele frequencies. Another normalized measurement of D is Lewontin's D prime, which is defined as the proportion of D to the most extreme value it could take given the allele frequencies. So, what is the difference between the correlation coefficient and D prime? We saw that when there are only two gamete types in the population, the correlation coefficient and D prime is 1. Let's come back to the simulation page. This time I want to consider a scenario in which the initial allele frequencies are different between the two loci. In this case, the initial allele frequency for big B at the second locus is set to half by default. And of course, I need to set the allele frequency for big A at another locus. Let's choose a value under half. Alright, this time there are three gametic types in the base population: big A, big B, little a, big B, and little a, little b. Although the population is in complete disequilibrium, the correlation coefficient equals 0.5. However, the D prime equals 1. Next, I want to set the initial allele frequency for big A to 0.6. The only difference is that in this run, we see big A little b gamete instead of little a big B gamete. So, when D prime is 1, it indicates that at least one of the four possible gametes is absent. Indeed, the correlation coefficient and D prime focus on different aspects of the gametic phase disequilibrium. The main use of D prime is that it measures the evidence for recombination between the loci. A value of D prime equals 1 can be interpreted as evidence for no recombination, while a value near 0 can be interpreted as evidence for considerable recombination. D prime can only be less than 1 if all four possible gametes are observed in the population. Okay, let's continue. The rate of disequilibrium declines as a function of the recombination rate between the two loci. As the last equation shows, d sub t is the coefficient of disequilibrium in generation t, d sub 0 is the value for disequilibrium in the base generation, c is the rate of recombination, and t is time in generations. In this run, I set the recombination rate to 0.5, which denotes the loci are unlinked. The amount of disequilibrium is halved by each generation, an equilibrium attained in less than 10 generations, as diagrammed in the graph. The frequency of observed gametes at equilibrium is equal to the product of the allele frequencies in that type of gamete. Let's run the simulation for 25 generations and set the recombination frequency to 0.1, which corresponds to closely linked loci. As appears in the graph, disequilibrium persists for many generations. In summary, under assumptions of Hardy-Weinberg, if the interested loci are in equilibrium, the gamete frequencies remain constant from one generation to the next. If the loci are in gametic phase disequilibrium, the equilibrium between two loci is not attained immediately, but gradually over several generations depends on the recombination rate. The higher the rate of recombination between the loci, the faster the population reaches equilibrium.